Hello everybody, welcome back to the lecture on the subject Applied Electromagnetic Theory. Myself Shyama Kumar, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. Today we'll be continuing with the lecture on electrostatics. In this lecture we'll be discussing electric potential, relationship between electric field intensity and potential, second Maxwell's equation, and electrostatic energy density. The next term we need to discuss in electrostatics is electric potential. So to define electric potential, first we are taking the work done to move a charge from one point to another. So we are trying to move a charge from point A to B in an electrostatic field. And this point A is at a position vector of RA and point B is at a position vector of RB. So we are trying to move a charge Q from point A to B. So according to Coulomb's law, we know that force on a charge Q is given by F equal to Q into E. So this is the force. Now we know that work done is same as force into displacement. So we are taking a small displacement dl along the path from A to B. We are not taking the entire length in the beginning, we are taking a small segment dl along the segment A to B. So the work done, differential work done in moving the charge over a small distance dl is force into distance. So F is a vector, distance is also a vector, displacement is also a vector. So it is F dot dl, and we are putting a negative sign because this work in moving that charge is done by an external agent. That is, the charge is not moving by itself. An external electric field or something is pushing the charge from one point to another. Now, if we substitute F equal to QE, we will get dW as minus QE dot dl. So this is the differential work done. Now, if you want to find the entire work done in moving the charge Q from A to B, so we will integrate it over the entire limit from A to B. So therefore, we will get W as minus Q into integral A to B E dot dl. So this is the total work done in moving the charge from point A to B. So now we have determined the work. Now if you divide the work by charge, that is the energy per unit charge, it is called as the potential. So the potential difference between 2 points A and B given by VAB, it is W by Q, and we have got it as minus integral A to B E dot dl. So this is the potential difference between 2 points A and B, and since it is W by Q, one of the unit you can use is joules per coulomb. Since it is potential, it is a voltage, so the unit can also be volt. Now when you consider the potential, here in VAB, A is the initial point and B is the final point. That is, if you are moving the charge from A to B, A is the first point and B is the second point. And when you consider the value of VAB, if it is negative, it means that there is a loss in energy when we are moving the charge from point A to B. So if there is a loss in energy, the work is done by the field itself. And if this VAB is positive, then it means that there is a gain in energy. That means an external agent will perform the work, thus it will have a gain in energy. Now when you consider the potential, it is independent of the path taken. That is, whatever be the path taken from A to B, it will just depend on the initial position and the final position. It will not depend on the path followed by the charge while it is moving from point A to B. So we have already derived the potential difference VAB as minus integral A to B E dot dl. So if you know the value of electric field intensity, we can find the potential difference. So in Gauss law, we have derived the expression for a point charge Q. Electric field intensity is given by Q by 4 pi epsilon r square AR cap. Now, when you substitute this expression into the expression for potential difference, we will get it as VAB is equal to minus integral RA to RB, where RA corresponds to the magnitude of position vector of point A and RB corresponds to the position vector of point B. Q by 4 pi epsilon r square, here we are having dot dr AR cap. That is, we are having a small length along the AR cap direction. Now, when you integrate it, we'll get the value as Q by 4 pi epsilon into 1 by R over the limit RA to RB. And from that, we'll get it as Q by 4 pi epsilon into 1 by RB minus 1 by RA. And when you separate the terms, the first term will actually denote the absolute potential at point B, and second term will denote the absolute potential at point A. Therefore, VAB can be written as VB minus VA. That is, it is the potential at point P, B with reference to A. So, it is the absolute potential. That is, VAB is the potential difference and VA and VB corresponds to the absolute potentials at point A and B. Now, we have derived the potential difference as difference between potential at point B and potential at point A. So for points, when we are considering point charges, we can choose infinity as the reference. That is, instead of taking a point as a reference, we are taking infinity as a reference. So if one of the point is made to infinity, that is, if point A is made to be at infinity, 1 by infinity, we will get it at 0. Therefore, the potential at point A will be equal to 0 as RA tends to infinity. Therefore, the reference point is infinity and the potential at infinity is assumed to be 0. Therefore, the potential at any point due to a point charge at the origin is given by Q by 4 pi epsilon R. That is, RB is made as R. Therefore, we will get the value of potential as Q by 4 pi epsilon R. So earlier we have seen potential difference. So to define potential, the potential at any point is the potential difference between that point and a point at which the potential is 0. So here we have taken that reference point to be infinity. Therefore, potential at a distance r from the point charge is the work done per unit charge by an external agent in transferring the charge from infinity to that point. So we are choosing the reference point to be infinity and we are bringing that charge to a point at distance r from the origin. So that is the potential V and it is given by minus integral infinity to R E dot dl. Earlier it was from RA to RB. Here we have made RA to be infinity and RB to be R. Therefore, potential is the work done in moving a positive unit charge from infinity to a particular point. So, when you consider the point charge, we have located it at the origin. If it is at some other point other than an origin with position vector r dash, that is, we are moving that charge from the origin. Then instead of Q by 4 pi epsilon R, we will have R minus R dash. So earlier it was simply R, that's the magnitude of vector R. Here we will be having R minus R dash if the point charge is not located at origin. So now we need to derive the relation between electric field intensity and potential. We already saw that V is minus integral E dot dl. So we'll try to derive a relation in terms of the del operator. And hence we'll derive the second Maxwell's equation. So here we are considering 2 points A and B which is placed in an electric field. And we are trying to move a charge from point A to B and it is moved back from B to A. So what we are doing is that when you consider the potential difference between 2 points, it is independent of the path taken. So when you consider VAB, it is actually VB minus VA. And when you consider VBA, it is VA minus VB. Therefore, we can write the potential difference between A and B. It is the negative of potential difference between point B and A. Now, if you bring this term to the left hand side, you'll get VAB plus VBA equal to 0. Already we know that the potential is the integral over A to B E dot dl. And this is integral over B to A E dot dl. If we substitute that value into this equation, we will get that this term reduces to closed integral L E dot dl, and that is equal to 0. It is closed integral E dot dl because we are moving from A to B and we are moving back from B to A. So it is a closed loop L and it is over the electric field dot dl. Therefore, we have got closed integral L E dot dl as 0, and this is the integral form of second Maxwell's equation. And it states that the net work done in moving a charge around a closed path in an electrostatic field will be always equal to 0. That is the statement for second Maxwell's equation. That is, if you want to move a charge around a closed path, we don't have to do any work. So therefore, we have got closed integral E dot dl as 0. That is, the work done in moving a charge around a closed path is always equal to 0. Now, the theorem or the law which relates a closed path is the Stocks Theorem. And according to Stocks Theorem, closed integral L E dot dl can be written as integral over surface del cross E dot ds. So this value is 0, therefore integral over S del cross ds is also equal to 0. Therefore, we'll get del cross E as 0, and this is the point form or differential form of second Maxwell's equation. So therefore, the equation, that is, if an electric field satisfies equation 1 or 2, we can say that the electric field is an irrotational vector or a conservative vector. Therefore, the electrostatic field is a conservative field. That is, it is independent of the potential, is independent of the path taken, due to which we will get the electrostatic field as a conservative field. Therefore, the second Maxwell's equation in integral form is given by closed integral L E dot dl as 0, and the point form or differential form is given by del cross E equal to 0. And according to the second Maxwell's equation, it states that the work done in moving a charge over a closed path is always equal to 0. Now, we will extend that derivation to find the relation between electric field intensity and potential. So, we already know that potential is V equal to minus integral E dot dl. Now, if you take the derivative on both sides, it is differential potential dV. So, this integral sign will be removed. So, we'll get it as minus E dot dl. If you take the three directions x, y and z, this E dot dl reduces to minus Ex into dx, minus Ey into dy, minus Ez into dz. That is the differential potential. Now, this differential potential can also be expressed as minus dou v by dou x into dx, minus dou v by dou y into dy, minus dou v by dou z into dz. That is, we are taking the potential as a function of x, y and z. So, if we take the derivative of potential with respect to x and multiply it with x, so the net effect from x, y, z can be combined to get the total differential potential. So, if we compare the two equations, we will get Ex as minus dou v by dou x, Ey as minus dou v by dou y, and Ez as minus dou v by dou z. So, it is the first order derivative of the potential along each direction. Therefore, electric field intensity is minus del V. That is, del operator, del V stands for gradient of a scalar. So, electric field intensity is negative gradient of potential. So if you find a gradient of the potential, you will get electric field intensity. And this negative sign indicates that the electric field intensity is in the direction opposite to the direction in which potential increases. That is, electric field intensity will be directed from higher to lower levels of potential. So now we will see a small example in finding the work done in terms of potential. So here we are given with the potential, which is 10 by r square sine theta cos phi. In the first part, we are asked to find the electric flux density at a particular point. Now this is having r, theta and phi, so this is already in spherical coordinate system. So to find d, we require electric field intensity. So E is equal to minus del V. So we'll take the expression for gradient in spherical coordinate system. So on substituting the value of potential into this equation, we will get the electric field intensity. That is, first term with respect to R, we'll take the derivative with respect to theta and with respect to phi. Thus, we will get the electric field intensity. Now we are having unknowns r, theta, phi. So we are asked to find d at a particular point. So we'll substitute that point into E. So at 2 pi by 2 0, if you substitute that value, sine pi by 2 is 1 and cos 0 is 1. So the first term will be 20 by 8 AR cap. When you substitute here, cos pi by 2 is 0. So this term reduces to 0. And the last term sine 0 is 0. So this also reduces to 0. So the electric field intensity is 2.5 AR cap and the unit of electric field intensity is volt per meter. Now when you find the electric flux density, it is epsilon into E. So when you substitute here, it is 2.5 into epsilon naught AR cap Coulomb per meter square. So on substituting the value of epsilon naught as 8.856 into 10 raised to minus 12 farad per meter, you will get it as 22.1 AR cap picocoulombs per meter square. And this is the electric flux density. Now in the second part, we are asked to find the work done in moving a charge from point A to B. So we already know that the work W is given by minus Q into integral A to B E dot dl, which is same as Q in the potential difference between point A and B. That is, it is Q into VB minus VA. So if you find the potential at point B and potential at point A, we can find the work done. So potential at A is the potential at 130 degree, 120 degree. So we'll get the value as minus 2.5 volt. And the potential at B is the potential at 490, 60. So we'll get it as 0.3125 volt. On substituting these values into the expression of W, we will get it as Q into VB minus VA. And on substituting it, we'll get it as 28.125 microjoules. So this is an example with the expressions for potential and work. So now we have derived potential and work done in moving a charge from one point to another. So the next derivation which we need to consider is for the energy density in electrostatic field. So our aim is to determine the energy required to assemble a number of charges. That is, we are bringing a number of charges from infinity and we need to place them at fixed points. So what is the energy present in that assembly of charges? That is used to find the energy density. So that is, we are finding the work done in bringing the charges from infinity and placing it at certain points. So here we are assuming that we are bringing charges Q1, Q2, Q3 from infinity and placing it at particular points P1, P2, P3. So we are bringing the three charges one by one. That is, initially this region is an empty region. It doesn't contain any charge particles. We are bringing the charges one by one from infinity and placing at those points. Initially, we are considering a charge-free region. First, we are bringing the charge Q1 from infinity and placing it at point P1. So, the system is initially charge-free. When you bring Q1 to the point P1, it doesn't require any work because there is no charge inside and there is no electric field already present inside the system. Thus, the work done in bringing the first charge is 0. Now, when you bring the second charge Q2 and place it at point P2, we need to do certain amount of work, and it depends upon the potential at the point 2 due to the charge which is already present at point 1. So, when we place the second charge, it depends on the potential at this point due to the charge which is present at point P1. Next, when you bring the charge Q3 to a point P3 from infinity, it will depend on the charge Q1 as well as Q2. That is, there will be a potential at P3 due to the charges at points P1 and P2. Thus, the total work done in assembling these set of charges is given by WE is equal to W1 plus W2 plus W3, where W1 is the work done in bringing charge Q1, W2 is the work done in bringing charge Q2, etc. So, this can be expressed as, that is, in bringing the first charge, the work done is 0, so W1 is 0. When you bring the second charge Q2, it is Q2 into V21, where V21 is the potential at point P2 due to the charge at point P1. So already we have brought two charges into the system. On bringing the third charge Q3, it is Q3 into potential at 3 due to the charge Q1 and potential at 3 due to the charge Q2. So this gives us the total work done in assembling the charge. So mark this as equation 1. Now we are trying to place the charges in reverse order. That is, first we'll place the charge Q3, then Q2 and then Q1. So in that case, when we place Q3 into the system is charge free. So the work done in bringing the charge Q3 into the system is 0. When you bring the charge Q2 into the system, there is already charge Q3 in the system. So it is Q2 into V23, where V23 is the potential at point 2 due to the charge Q3. And when you bring the last charge Q1 into the system, it will depend on charges already present at P2 and P3. So it is Q1 into V12 plus V13, where V12 is the potential at 1 due to Q2, and V13 is the potential at 1 due to charge Q3. Mark it as equation 2. On adding equations 1 and 2, we will get it as 2WE is equal to Q1 into V12 plus V13 plus Q2 into V21 plus V23 plus Q3 into V31 plus V32. When you consider this V12 plus V13, it can be rewritten as V1, which is the total potential at point P1. And V2, it is the total potential at point P2, which is the sum of V21 and V23. Now the last term is V3, which is potential at point P3, which is the sum of V31 and V32. Therefore, we will get WE as half into Q1V1 plus Q2V2 plus Q3V3. That is, if the system is having three charges, V1, V2, V3 is the total potential at points P1, P2 and P3. This gives us the total work done in assembling a set of three charges. Thus, we can generalize the equation for work for a system of n charges as WE is equal to half into summation k equal to 1 to n Qk Vk, where Qk denotes the charge n point charges and Vk is the potential at points P1 to Pn. Now, this is the case when we are considering discrete charges. Now, if we are considering continuous charge distribution, this summation changes to integration. So, if we are considering a line charge, this instead of Q, we'll have integral over rho L dl. That is line charge density, and we should integrate it over the total length. So, this summation changes to integration, and instead of point charge we are having a line charge. So we are having integral over L rho L into V dl. Instead of line charge, if we are having surface charge, it will be rho S into V ds. And for a volume charge, it is rho V into V dV. So this is the expressions for work if we are considering continuous charge distribution. Now we are trying to generalize the expression by considering volume charge. So for a volume charge, we are told WE is half integral over volume rho V into V dV. Now we have already learned Gauss law. According to Gauss law, del dot D is equal to rho V. So substituting rho V as del dot D, we will get WE as half integral over volume del dot D into V dV. So this is the total work. Now we have an identity for a vector A and a scalar V as del dot A into V is equal to del dot VA minus A dot del V. So here we have got an expression similar to the LHS of this side. Here the vector A is equal to D. So on applying this identity, we will get WE is equal to half integral over volume del dot VD dV minus half integral over volume D dot del V dV. So this is the simplified expression for WE. Now we have reached the equation WE as half integral over volume del dot VD dV minus half integral over volume D dot del V dV. So when we consider the first term in the RHS, we can apply the divergence theorem. We are taking the divergence of a vector. So according to the divergence theorem, this del dot VD into dV, this can be expressed as a surface integral of the vector VD dot ds. So we have applied divergence theorem to the first one. Second term, it is kept unchanged. Now, when you consider the first term, we are having Vd dot ds. So already we have learned the potential and flux density for a point charge. So when you consider a point charge, the potential is inversely proportional to R and the flux density is inversely proportional to R square if you are considering point charge. Now if you consider a set of two charge called as dipole, then the potential varies as 1 by R square and flux density varies as 1 by R cube. So as the number of charge increases, the power of R also increases. Thus, on a minimum, V into D will vary at least by 1 by R cube. Minimum it is 1 by R cube and area will be always proportional to R square. So if you consider this term, integral over SVD dot ds will be directly proportional to a minimum of, if you consider a point charge, it is 1 by R into 1 by R square and area will be proportional to R square. So it will be inversely proportional to R. And as R tends to infinity, that is if you are considering large distance, then this term tends to 0. So the first term in the equation can be neglected if the distance is large. Therefore, the first term in the expression is neglected since it is very small for large surface. Thus, we will get WE as minus half integral over volume D dot del V dV. You already know the relation between electric field intensity and potential. E equal to minus del V. So if you substitute del V as minus E, we will get WE as half integral over volume d dot E into dV. So this is the work done which depends upon the electric field intensity and volume if we are considering volume charge distribution. Now we know that B is equal to epsilon E. So on substituting B as epsilon E, we will get epsilon into E dot E. If we are taking the dot product between two same vectors, it will be equal to magnitude E square since the angle between them is 0. Therefore, the electrostatic energy in joules, that is WE in joules, is given by half integral over volume d dot E into dV. Now, if you consider this d, we can substitute it as epsilon E. So, epsilon into E dot E. So, E dot E means we are taking the dot product between same vectors. So, you'll get it as magnitude of E square. So, same, it can be replaced as half integral over volume epsilon magnitude of E square dV. Now, when you consider this magnitude of E square, it can be written as magnitude of d square by epsilon. D square by epsilon square. So 1 epsilon gets cancelled. So it is d square by epsilon into dV. So this is the electrostatic energy in joules. Now we are finding the electrostatic energy density. The unit is joules per meter cube. It is the work done per unit volume. So we need to find dWe by dV. So if we take the derivative and divide it by dV, we will get electrostatic energy density denoted by small we. So if you take the derivative, these integration signs will be removed. And if you divide it by dV, you will get it as half into d dot E or half epsilon E square or d square by 2 epsilon. So this gives us the expression for electrostatic energy density. It is the energy per unit volume. So now we'll see an example to find the energy in a system of 3-point charges. So we are having 3-point charges minus 1 nanocoulomb, 4 nanocoulomb and 3 nanocoulomb, which are located at 000, 001 and 100 respectively. So since there are 3-point charges, we will use the expression half into Q1 V1 plus Q2 V2 plus Q3 V3. Now V1, V2, V3 represents the total potential at point 1, 2 and 3. So when you substitute the values of V1, it is the total potential at 1 due to charges Q2 and Q3. So it is Q2 by 4 pi epsilon R2 plus Q3 by 4 pi epsilon R3. Similarly, when you consider V2, it is a total potential at 2 due to Q1 and Q3. So it is Q1 by 4 pi epsilon R1 plus Q3 by 4 pi epsilon R3. Similarly, when you consider V3, it is a total potential at 3 due to charges Q1 and Q2. So it is Q1 by 4 pi epsilon R1 plus Q2 by 4 pi epsilon R2. Now, when you observe this equation, this R1, R2, R3 represents the distance vector between 2 points. So R2 will be the distance between Q1 and Q2. R3 will be the distance between Q1 and Q3. R1 again is the distance between Q1, Q2, etc. So in using that case, we will get the value of R1, R2, R3. Now, on substituting the values of Q1, Q2 and Q3, we will get the total energy in the system as 13.37 nanojoules. So here we'll see one more example in which we are given the potential function in Cartesian coordinate system where V is equal to 2x plus 4y volt. Now we are asked to find the electrostatic energy density within a volume of 1 meter cube. So since we are having potential, we need to first find electric field intensity so as to find electrostatic energy density. So electric field intensity can be determined as E equal to minus del V. So it is equal to minus dou v by dou x ax cap plus dou v by dou y ay cap plus dou v by dou z az cap, which is the expression for gradient in Cartesian coordinate system. So when you substitute the value of potential, when you take the derivative with respect to x, you will get 2. So it is minus 2 ax cap. When you take the derivative with respect to y, it is 4. So it's minus 4 ay cap. And when you take the derivative with respect to z, it is 0. So you will get it as minus 2 ax cap minus 4 ay cap volt per meter. Now, when you're finding the electrostatic energy density, is the energy per unit volume. We have already seen the expression small we is equal to half epsilon into magnitude of E square. So first we'll find the magnitude of E. So magnitude of E is root of minus 2 the whole square plus minus 4 the whole square. So you will get magnitude of E as root of 20. On substituting this value into the expression, you will get, since the medium is not specified, we'll take it as, it is specified as free space, we'll take epsilon equal to epsilon naught. So it is half into 8.854 into 10 raised to minus 12 into magnitude of E square. So it is 20. So you will get it as 8.854 into 10 raised to minus 11 joules per meter cube. That is the value of electrostatic energy density. So we will conclude this lecture on electrostatics. In this lecture, we have discussed about potential, relationship between electric field intensity and potential, second Maxwell's equation, and the derivation for electrostatic energy density. Thank you.